For joining us today for this introductory webinar on laser vibrometry. It's not designed to be a masterclass in laser vibrometry, more an introduction for those people who are not familiar with this technology. And so the slides don't attempt to get into any particular application in any great detail. It's just designed more as an overview to give you some ideas as to how laser vibrometry might be applied in your particular field. So what I'm going to do is I'm going to show you some slides. I'm going to talk about Polytec, describe Polytec, how we first got involved in laser vibrometry, talk about the technology, how it works, some of the key benefits that are being enjoyed by our many thousands of customers worldwide. We've been supplying laser vibrometry now since the 1980s, so we have a huge depth of knowledge and experience in this field, and as a consequence, we also have a very broad product portfolio, many different configurations, and many applications that those configurations make possible. I'm also going to briefly introduce full field scanning laser vibrometry. It'll be covered again in the talk that I'm giving on Thursday, which will focus more on the ultrasonic frequency end of the spectrum of measuring vibration. I'm also going to briefly mention a special version designed to test structures that can only be seen through a microscope, all the way up to an industrial robot-based system for fully automated modal analysis of structures like a vehicle or like an airplane, or even smaller structures too. But because it's robot-based, it allows measurements in a fraction of the time that it would normally take using conventional accelerometers, even faster than a regular scanning vibrometer. So I'll give you some examples of the many different ways this technology can be applied. And as I said earlier, I'll hopefully seed some ideas as to where laser vibrometry can be used in your company or university to satisfy your own particular needs. So, of course, vibration is everywhere. It's in the cars that take us to work every day. It's in our computers. It's in critical weapon systems that have to be accurate and reliable to help keep us safe. It's in household appliances. It's in the vibration of small bones and hairs inside our ear, ossicles, and the cochlea inside our ear. It's in turbine blades and jet engines. I mean, it's basically everywhere, and that's kind of what makes our jobs very interesting, because we get to be involved and to develop relationships with a very diverse range of customers and learn some very interesting applications. It's used to help improve products, to help make them quieter, help make them safer, make them perform better, and to help find defects in the production line. We have a very proficient system called the IVS 500, which is used extensively in production testing of various devices, and I'll touch on that as well. All of these can result in products becoming more attractive, performing better, leading to greater market share and sales volume. So vibration is a particularly important subject to address in many different applications. And in many of these examples, we find vibration. There's also a need to, of course, measure vibration. And some of the techniques that we use to apply to solving these problems are listed here. So, for example, performing modal analysis to investigate structural modification scenarios or to extract parameters required to validate or calibrate finite element models, because we can't completely depend upon finite element models depending on the kind of assumptions that are made in the model, especially when it comes to refining the models to the sort of clarity and resolution that is necessary to more accurately predict what's going to happen to a structure, a device, or a product in more extreme conditions and more realistic conditions than can be represented in a laboratory setting. So it's also used for transducer development, used in medical devices for optimization of their performance. It's used for studying stress and strain. You can compute strain from the vibration measurements, because we not only measure vibration in the direction of a single laser beam, we can, by using multiple lasers, we can measure three-dimensional vibrations and extract from that the strain distribution across a surface, where strain gauges or digital image correlation techniques just don't have the vibration or the strain resolution or the frequency bandwidth that can be achieved with laser vibrometry. It's also used for visualizing wave propagation during the study of Lamb waves for non-destructive evaluation, and as I mentioned, in inline quality control. We are the undisputed world leader in optical measurement of vibration. We were founded 51 years ago now. We were founded in Germany, and we set up a US subsidiary in 1978. So we are celebrating our 40th anniversary in the United States this year. We have around 400 employees worldwide. A very large percentage of them are involved in research and development. And we've been involved in vibrometry since 1986. So we have a huge depth of knowledge and experience, and product line to support that depth of knowledge and experience. Our products are very reliable, very high performing, and we literally have thousands of satisfied customers throughout North America. And we are truly recognized as the gold standard for non-contact measurement solutions. We have 4 main offices in the United States. I'm speaking to you from Hudson, Massachusetts, and where we perform our calibration services. And we have other offices in the Detroit area, in the Southern California area, and various other offices, home offices scattered around the country. Now we, as I mentioned, we offer laser Doppler vibrometers for non-contact vibration measurements, but that's not the only optical measurement solution that we offer. We also produce laser surface velocimeters, or LSVs, for measuring surface speed and length, and also surface profilometers for measuring surface topography or profiles, roughness, waviness, form, or step height applications. And the surface profilometry technology can be integrated with laser Doppler vibrometry for measuring surface profile in MEMS measuring or microstructure measuring systems for looking at miniature objects only visible through microscopes. We also sell what's called an acoustic camera that uses beamforming techniques together with microphones to identify noise sources and characterize those noise sources full field. But today I'm going to be concentrating on laser Doppler vibrometry for non-contact vibration measurements. Technology detects a Doppler shift. So that's the shift that you hear every day when a vehicle passes you on the highway. The acoustic effect is heard when vehicle goes by and you hear a change in the tone of the sound generated by that vehicle, an ambulance siren, for example. It also contains a high precision laser interferometer, and it provides accurate and precise time-resolved output proportional to displacement or velocity in the direction of the laser beam. We also have data acquisition systems, software for processing the signals. We have hardware for scanning the laser beam across the surface, and software for doing a variety of very complex, useful tasks. For example, importing finite element model, exporting to a finite element model for validation, or importing a finite element mesh, coarse and mesh, for defining the measurement points for performing the test. This slide shows one of our most recent laser vibrometers, which I'm going to be talking about in a little bit more detail in a couple of slides from now. So again, the technique is analogous to the acoustic effect, and here you see as a vehicle approaches you, the sound waves that it's generating are compressed, and the sound waves coming out of the back of the vehicle as it moves away from you are extended. So there is a very simple relation between the frequency shift that occurs, delta FD, and the velocity that the car is moving at. And in the case of a laser vibrometer, the wavelength of the laser that we're using for measuring the vibration. So if we know the wavelength, lambda, and we do very precisely because we use, in most cases, a helium neon laser. Any lasers have very stable, very accurately understood wavelengths. So we know lambda. If we can measure the frequency shift, then we can calculate the velocity v of the surface. So here is a simple laser vibrometer. Aim a laser at let's say a tuning fork. It generates a voltage proportional to velocity. We can also look, and that velocity is derived, as I said, from the frequency shift in the reflected light. We can also look at the change in the optical phase of that reflected light to convert the electrical signal to voltage proportional to displacement. And with this technology, we can achieve resolutions better than a picometer, and in terms of velocity, better than 5 nanometers per second per square root hertz. And this is orders of magnitude, depending on the field of view, better than digital image correlation, which is another technique for providing full field measurements of vibration. So very high resolution and very wide bandwidth. We can achieve bandwidths up to megahertz, even gigahertz with this technology without losing resolution. Without losing resolution also with field of view, with distance from the object. So we achieve the same resolution whether we're a foot away or whether we're 10 meters away with an area scan of, let's say, 3 meters by 3 meters if we were interested in scanning a large area. So back to the principle of operation. We use a laser which we split into 2 beams. One beam goes out to the target that's vibrating. Another beam passes through what we call a Bragg cell. That introduces a frequency shift in the light, or in other words, a kind of a slight color shift in the light, so that when some of the light is scattered back from the vibrating surface, re-enters the interferometer, and then passes through and merges with the light that's passing through the Bragg cell, you get constructive or destructive interference depending on the relative path length between the 2 surfaces. In this case, though, because we're introducing a frequency shift, what we see is a frequency shift. So we have a signal of the photodetector that's, in the case of a 40 megahertz Bragg cell, is a 40 megahertz signal plus or minus FD, where FD is the frequency shift introduced by the vibration. So again, if we can measure this frequency shift, we can calculate V, which is the vibration velocity amplitude. And we do this with a very sophisticated FM decoding system. Typically, it is in a separated controller, so we have our optical head, which can be very compact. It can be mounted separately on an optical table or on a tripod, or because it's separated from the electronics, very flexible in positioning and aligning. Then we have the controller where we do the FM decoding. We have various filter settings and range settings, bandwidth settings that we can select in the controller. And we can output velocity, displacement, and in some of our systems also an acceleration signal. Then we can take that signal just as we would an accelerometer signal, perform an FFT on it to extract the resonant frequencies of a structure, for example. So we have typical components of a LDV. We have the sensor head, we have the control electronics, and then we have the data acquisition system. And so one data acquisition system we provide is the VIPSoft system, and that has integrated with it the ability to capture video, because some of our vibrometers, such as this one for outdoor long-range measurements, has a video camera built in, so that you can very conveniently see exactly where the laser is measuring without having to guess. You know, if you're outdoors, you really can't see these lasers because, of course, they need to be eye safe, and so they're basically invisible. But their location can be identified with the inbuilt video camera. So we have a laser source, interferometer optics, data acquisition system, and control electronics comprising the one system. We have different configurations of laser vibrometer. We've got what we call our single beam laser vibrometer, where we're measuring the vibration in the direction of the laser light. So this is an example of that, which I'll be talking about in a couple of slides. We can take that one step further. Instead of having one laser, we can have multiple lasers. And this is our MPV, multi-point vibrometer, that's available in an array of up to 48 lasers that can measure simultaneously. And we can take those signals and we can make sense of them and provide visualization of deflection shapes, export the data for finite element model validations, and so on. We have our differential vibrometers, which measure the relative vibration between 2 points. So one point, let's say is on a valve in an internal combustion engine. The other laser is aimed just adjacent to the valve, so that we can measure the true closing velocities and bouncing of the valve as it meets that background. Scanning vibrometers take the single beam, and we use typically galvanometer mirrors to drive the laser beam from point to point in a sequential method. This is our PSV 500 system, and here's a video, again a video image of the car in this case, with the mesh that is defined visually, in this case manually, for scanning those points. But we can also import the mesh from finite element model to scan those points as well. We have 3-axis vibrometers. This is where we have 3 lasers aimed at a single point, where we use triangulation to extract the velocity vectors in X, Y, and Z. And that's one example there that I'll be talking about later. Then we have our 3-axis scanning, which takes those 3 simultaneous lasers aimed at a point, and we move that point around. So the 3 lasers are synchronized so that they can scan the same point from 3 directions, and then that point can be moved around. And in this case, we have our robot system, where we can use the scanning mirrors inside the heads here for scanning a certain region, and then use the robot to move the scan heads to a different area to scan a different region, and then use stitching to stitch together all the data into a single file for the entire vehicle. Then we have our long-range vibrometer, which you saw in the previous slide. So we cover truly the range from microstructures on the right to large areas on the left, using a microstructure vibrometer here, for scanning, single point for version, and our scanning version for large areas down here. And in the middle we have a large area scanning vibrometer with a close-up attachment, so we can measure objects that are smaller than, say, the size of a business card. So yeah, we can truly cover the entire spectrum, not just in terms of frequencies of vibration, but in terms of area of view or size, dimensions of the structure. And here's our robot-based vibrometer. I mentioned I would go over the new MLV system, new laser vibrometer that we have. It has built-in autofocus. It has what we call extra optical sensitivity, which means instead of using a red laser, it's using a near-infrared laser. The advantage of using a near-infrared laser is that we can boost the output power while maintaining eye safety. So we can get a higher power laser impinging on a surface, which means that even for very poorly reflecting or very distant surfaces, we get sufficient return signal to make a very high resolution signal-to-noise measurement of the vibration. So it's particularly applicable for extreme applications where you get very poor reflectivity from the surface. It has a range that's higher than the predecessor, the 505 5000 system version that we continue to sell, helium neon based, because there are many applications that require the red laser. There are other applications that require the near-infrared laser, so we've maintained the product line to give us that flexibility depending on the application. The Heaney version has a maximum velocity of plus minus 10 meters per second. In some configurations, in others, it has different amplitude ranges, but because we're moving to a longer wavelength, we have a wider amplitude range too. Similar size, shape, and weight to the OFV 505, the helium neon, the red laser system. Again, the head is separated from the control electronics I mentioned earlier, the advantages of doing that. Exchangeable front lenses. It has a fiber optic accessory with 8 micrometer minimum spot size, so we're looking at really small devices, and 22 velocity ranges. So why LDV? What are the advantages of LDV? Now, what I'm really highlighting here are the advantages relating to accelerometers, which is the conventional way of measuring vibration, performing modal analysis, for example, falls into really 3 categories. Higher accuracy, because you're not adding any mass, you're not adding any stiffness, it's all done through light. And in the vast majority of cases, you don't even need to apply any kind of surface to scatter the light, because surfaces are scattering the light naturally without typically any surface preparation. Unlike years ago when laser vibrometers required some kind of a dull or surface coating. So these days they really don't. They achieve sub-micrometer spatial resolution, picometer displacement resolution, frequency dependent, temperature independent, unlike accelerometers, which are very frequency and very temperature dependent. They're pre-calibrated, which is also an advantage over digital image correlation. You don't have to perform a calibration, and the resolution of a laser vibrometer is unaffected by distance or and it's also unaffected by the field of view. The second major category is cost and time savings. It's literally you aim a laser and you measure the data, you get an output proportional to vibration. Laser can be scanned, it's very fast, very easy to operate, and there's only one transducer to calibrate. There's no special software processing required to get a result. You literally get a result instantaneously. Measures in vacuum through windows, high frequency, large amplitude, hot, lightweight. Many different applications can be enjoyed with laser vibrometry versus accelerometers. So just looking at these in a little bit more detail, the technology truly is point and shoot, as I mentioned. Frequency, in terms of frequency range, because we can measure up to megahertz or even into the gigahertz range, it allows us to use our technology for medical ultrasonics, developing new ultrasound transducers at high frequencies, apply it to, our customers apply it to RF MEMS, non-destructive evaluation, for example, using lasers to excite the structure, all the way down to very low frequencies, gossamer structures like solar sails and inflatables for space deployment that have their resonant frequencies perhaps well below 1 Hertz. Very high amplitudes, 30 meters per second, which allows you to measure pyroshock, explosive testing, Formula One engines. Several teams, NASCAR teams, utilize our technology. Hot surfaces, looking at automotive exhausts, jet engines, rocket motors. They're used underwater, on naval structures, sonars, subs, torpedoes, biological surfaces, MEMS devices, through windows, environmental testing, on delicate structures for entomology, studying insects, lightly damped airfoils, hearing. Again, I mentioned the basilar membranes earlier, and MEMS devices. Here's a comparison with accelerometers. You see accelerometer response on a turbine blade, and if you remove the accelerometer and you measure the exact same location with a laser vibrometer, you get quite a different result. You can see that in this case the frequency is not affected, but if you look at some of these other frequencies, they're very strongly affected. Not only the resonant frequencies are shifted, but also the amplitudes of this response are shifted tremendously. So very significant benefits for using a non-contact approach. Laser can be scanned up to 250,000 points. I'll talk about scanning vibrometry in a couple of slides. We also have a multi-point vibrometer that allows you to measure up to 48 simultaneous points. Again, 2.4 gigahertz is a maximum frequency range, 40 meters per second. It can be used on red hot surfaces. For submerged structures, you have to take into account the refractive index of the fluid that the surface is submerged in. So if you're using water, for example, you would have to divide your results by 1.33. So that, I think, is the only situation where the calibration is affected. Otherwise, it's not affected by temperature, frequency, distance, field of view. It's just the refractive index of the medium, which actually gives you a larger signal for a higher refractive index that you might observe with water or fluids. It'll go through windows, so that's especially useful. You have to be a little careful that you are measuring the device behind the window and not the window itself. So we advise aiming the laser at a slight angle to the window so that the strongest reflection comes from the device you're testing and not from the window. Otherwise, you'll be measuring the vibration of the window instead. Here we have an example of frescoes being measured with the laser vibrometer. In the lower half of the slide there in the middle. Just again giving you an example of the tremendous range that vibrometers enjoy. Single point solutions, some single point solutions are shown here. I already talked about the MLV. The 534 is configured here on a test stand with a stage, and you can see that it is configured with microscope objective. So this is especially attractive to universities who want to cover a very wide span of uses from microscopic to macroscopic. So you could add a microscope lens to look at tiny devices, or you could remove the microscope lens to measure longer distances, larger structures. There's a built-in camera option. So again, here's the camera image. So you can see exactly where the laser is being positioned on the structure. There's also side exit probes for this system, and also illumination units. So you can actually send illumination down through the objective, so you can actually see more clearly where more light is required. Here's our portable digital vibrometer. There's a laptop configuration, so it's truly portable. This is like an old-fashioned video camera, but it has everything built into it. I meant the size of an old-fashioned video camera, but it has all the electronics built into it. So it's powered with either the 120 volt mains power, or you can get battery packs to power this, so it truly can be used in the field. And here's an interface here so that you can connect to a laptop for data acquisition using the VIPSoft system. Here's the bridge testing slide using the long-range laser vibrometer from a distance of 108 meters, or rather the bridge was 108 meters above the river, and the measurement was made from a distance of 140 meters, and the train was exciting the bridge as it passed across. So you can see a very clear displacement of the bridge while the train travels over it. This is an example where the goal was to determine the Young's modulus as a function of temperature of a tungsten filament, studying different tungsten filament materials that would be used in target systems of next generation high power particle accelerators. And the filaments were measured through a window, and you can see the window right here using the vibrometer you saw in the previous slide, the OFI-534. You can see a close-up of the window, as said here, with the wire behind it. Here's an example of dual beam measurements with the high-speed laser vibrometer on an engine, a car engine, for valve train testing, measuring the relative movement between the valve and the valve seat. So you're removing any background vibrations of the engine block. So you can see very precisely, very accurately what is happening when the valve closes against its seating surface. And you can see here that a 12 kilohertz bounce signal is revealed in the measurement. We have rotational vibrometers. This is our RLV 5500. Again, there are two beams involved. One beam is aimed one side of the rotational axis. The other beam is aimed at the other side of the rotational axis. And you get essentially three outputs. You have a DC value proportional to the RPM of a shaft. The second output is an angular velocity signal, and the third output is an angular displacement signal, which is actually derived by integrating the angular velocity signal, but it's a real-time output. And it can be used for order tracking, crankshaft, prop shaft. You don't have to aim the lasers onto a circular surface. You can, for example, aim them onto a hexagonal bolt head at the end of the shaft. So very flexible system indeed. We have two beam separation to choose from, 7.5 and 24 millimeters. The different beam separations allow you to measure different shaft diameters, give you different resolutions and different ranges of vibration. Measures angular displacement and velocity up to 20 kilohertz. And obviously the advantage of a system like that is that you don't have to attach anything to the shaft. You don't need encoders. It avoids the downtime in having to attach decoders to perform essentially the same measurement. This is an example of a 3D vibrometer where we're measuring vibration from 3 directions at a single point. In this case, we don't have 3 lasers aimed at the same point. We have only 1 laser, and we have 3 interferometers that are aimed at that point. So again, through triangulation, we can extract velocity vectors x, y, and z. And here we have a scanning stage, so we can actually scan the device under the laser beam and map the 3-dimensional vibrations over a full surface area. And here's an example of a measurement on microstructure. With that system, you can see the 3 spectra that were measured at that identified location right there. And here's an animation of the response at 21 kilohertz. So it's mostly an in-plane rotation occurring at that frequency, but you can see some out-of-plane vibration occurring at the same time. Moving on to scanning vibrometers now. With a scanning vibrometer, we have the laser that we then scan using steering mirrors. These are galvanometer-driven steering mirrors. Excuse me, go back to that slide. And they scan the laser in a sequential way from point to point to point to point, acquiring the vibration response at each point. They simultaneously gather the reference signal, so we can measure the relative phase of each scanned point with respect to a fixed reference that can come from an accelerometer or a force gauge if you're using a shaker to excite the structure, or another transducer attached somewhere, or maybe a microphone to give you your fixed reference. So with that fixed reference and the scan laser, we can calculate and display animated deflection shapes, color-coded animated deflection shapes of the structure. And if we excite with running condition or broadband excitation, then we can study what's going on in the test object across a complete spectrum of vibration. This is kind of a condensed slide, just summarizing the benefits relative to accelerometers as they apply to laser vibrometry, scanning laser vibrometry. So again, no mass, no added dampening, no stiffening. Lasers can be scanned, so it's much faster. It can be used through windows, fluids, high temperatures, so it opens up new applications. There's no cabling on the structure, so again, no added mass, no added stiffness from the cabling. We can get a very small spot, much better spatial resolution. We can import the FE geometry, so there's no uncertainty as to where the correlation is taking place between the measured data and the simulated data. There's only one, or in the case of a scanning 3D vibrometer, only 3 transducers to calibrate. There's no accelerometer roll-off or resonance at, let's say, 5, 10, 15, 20 kilohertz. The vibrometer response is extremely flat across its full bandwidth. And there's no spatial anusing typically involved because we can afford to scan many, many more points than you can analyze with an array of accelerometers, simply because it's impractical to do so using that other technology. So here's an example of what happens when you take fewer and fewer points. If you have a high density array of measurements and you look at the line profile down the center of the measured data, you get 19 points. You get a very precise wave shape. Amplitudes are very precise. The fewer points you take, the more you get an error in the amplitude, and the more you get a distorted shape. So that if you're using 5 points, which might be the case if you were limited to the number of accelerometers you could attach, you see a very, very different result that that isn't necessarily obvious from first view. So scanning vibrometers measure up to 250,000 points. They're measured sequentially. There's software built in to provide a signal generation for shaker, for example. There's data acquisition, display manipulation. We can import the geometry file, or we can measure the geometry. We have a geometry measuring option, uses a time-of-flight laser to scan the object to give us a measurement of the profile that we can also export with the finite element model correlation data, measured data from the vibrometer. These systems have bandwidths up to 25 megahertz, and they're available in 1D or 3D form. So we've got a 1D system. We have 1D systems that can be upgraded to 3D systems, so 3D ready 1D systems. And 1D systems are used for operating deflection shapes, acoustics, rotating structures. And when you move to the 3D systems, you're talking about more complete, sophisticated data for doing modal analysis, FEM validations, stress strain calculations, and so on. So here's an example of a 3D measurement on a vehicle, and just give you an idea of the sort of density of measurements that can be achieved. Much higher density than would be attempted using accelerometers in a small fraction of the time using accelerometers. So if we take that one step further to a robot-based 3D measuring vibrometer that can rove all around the vehicle, we scan a certain area. We then use the robot to move the three heads to a different area and repeat the scan. So the system knows from the vibrometer, from the robot, exactly how far those three heads have moved. So we can very easily take all that position data, combine it with the vibration data, and get a full three-dimensional map of the entire visible surface of the vehicle. And those data can be integrated with measurements from hidden points that could not be reached with a vibrometer from, say, accelerometers that are maybe mounted inside the vehicle somewhere where you can't get laser access to those surfaces. So the RoboViv system performs, let's say, on a vehicle body and white inspection for modal analysis. Say the setup would be maybe during the daylight hours, and then you would have it running overnight. So in a 24-hour span, you could get results, density of which is far greater than you would expect to achieve using accelerometers that might take 3 or 4 weeks to achieve using the contacting technology. So not only do you get better definition, better resolution, better accuracy, but you also get it in a tiny fraction of the time that it would otherwise take using conventional methods. So to give you an idea of what can be achieved with laser vibrometers, here the goal was to validate a finite element model. A 2,000 point coarsened FE grid was imported for performing the measurements. Accelerometer was used for the phase reference. There was no surface preparation of this surface because the PSV 3D Extra was used, so very high optical sensitivity, doesn't need reflectivity, and B, you wouldn't want to put any kind of a powder or diffusing surface on the brake anyway, because it would completely affect the measurement. You don't want to contaminate the surfaces at all with something that would change the friction properties of the brake. So ported the grid, coarsened the mesh, heads were moved to different locations, and the data was stitched from different directions. And here is the result. Hopefully you can see this animation on your computer screens. And again, very high resolution, very high density of measurements. It kind of looks like it's model data, but it's actual real experimental data that can be used to validate the model very, very precisely. It's simply impossible using conventional accelerometers, and also DIC, because DIC requires a surface finish and also simply just doesn't have anywhere close to the resolution that can be achieved with laser vibrometers. Here's our multi-point vibrometer, measured up to 48 points, 100 kilohertz bandwidth, 1.75 meters per second velocity range, and it's integrated with the exact same software that we developed for the scanning vibrometer, only we're measuring those 48 points simultaneously. So we can do operating deflection shapes, we can do time domain animations, and so on. And here's an example of a measurement on a 9-iron golf club face, and the shaft. 24 measurement points. All points were measured simultaneously, and here are the different deflection shapes that were measured from the frequency spectrum. Here's the frequency spectrum down here. So here's resonance 1, 2, 3, 4, and 5, and here are the corresponding deflection shapes, again from a single impact of the club face. And here's a time domain animation of the golf club. The first 1.5 seconds worth of response, showing rotation of the head at 5.4 hertz. And here is the same 9-iron, but just the first 25 milliseconds. So you can see the wave propagating from one end, there goes and bounces back, and then back and back as the vibration proceeds. So very interesting to study how the vibration gets into the hand, maybe changes the feel of the golf club. I showed this briefly in one of the slides earlier, but here we have the MSA 600. Excuse me, I didn't update this slide. We have now the MSA 600 that was introduced earlier this year, combining 3 technologies in one. Laser vibrometers for measuring out-of-plane vibration, using scanning vibrometry. In-plane motion is measured using stroboscopic video microscopy technique. I'm not going to talk about that in detail today. And the profile is measured using white light interferometry, so you can get surface profile or topography of the surface. Here is our micro small systems measurement system. It's for those who are budget conscious but need to measure microstructure devices. Is again stage-driven scanning with our OFE 534 you saw earlier with a microscope. So we can measure microstructures or small devices, again with the same scanning software that was developed for the PSV systems you saw before, but in a smaller package. Bandwidth up to 2 megahertz, up to 50 millimeters square area can be measured, and it has the integrated video like I mentioned before. So that brings me to the very last slide, just to mention that we not only offer our technology for those who want to invest in purchasing our equipment, but also for those who maybe can't justify an investment of that magnitude, and maybe want to evaluate the technology for to build a case to management to invest in technology, or maybe they just have such occasional requirements that it can never be justified to invest in a capital acquisition. So we can offer any of our systems, either for rental, where we train you and you perform the measurements, or we can come along with our application engineers who are fully trained, fully experienced in these systems to perform the measurements on your behalf. So you have access to the entire portfolio of equipment, the convenience of testing either at your facility or ours, and short notice requirements. You don't have to wait to get the budget to buy a system for delivery of the system. Just give us a call and we will schedule your project in with our availability. And as I said, it could also allow you to evaluate the systems just in case you want to justify purchasing a system down the road. So that brings me to the end of my presentation.